In this video, we'll be learning about the inverse trig functions. Remember that a trig function, or a trig ratio, compares the sides of right triangles in relation to the angle theta. The inverse trig function will help us determine the measure of that angle theta if it's not given to us. So when you know what the sine of A is, if it equals a variable x, then if you take the inverse sine of that amount x, then you will get the measure of the angle A. If you know cosine of angle A equals x, then the inverse cosine of x equals the measure of angle A. And if you know tangent of A equals x, then the inverse tangent of x will equal the measure of angle A. This is another function that we will use on the calculator, and we want to make sure that our calculators are set to degree mode. So we're going to look at how this works. If this is our given triangle, and it looks like in these examples I'm solving for the measure of angle A, that means that my A is my theta. So in relation to theta, the side across from it is the opposite, the side next to it is the adjacent, and the side that is across from the right angle is always your hypotenuse. So remember that the sine of A, sine is always your opposite over your hypotenuse. The SOHCAHTOA, it's SO, that first abbreviation that we use. So the sine of A in this triangle would be the opposite side BC over the hypotenuse side AB. Well, I want to figure out what is the measure of angle A. So this is where we'll use the sine inverse, and we'll take the sine inverse of both sides of this equation. So it's like when you take the square root of something to undo a square. The sine inverse is that inverse operation that will undo it, and that means that this sine inverse and sine function basically cancel each other out, leaving us just with an A, and on this side it's a value that we can find. So the inverse sine of BC over AB will equal the measure of angle A. So this becomes the formula that we're basically using there. So the sine inverse of the opposite over the hypotenuse will equal the measure of angle A. So you're still using opposite and hypotenuse there, but it will help us figure out what that measure of angle A is. Your cosine inverse, same idea. Start with your cosine ratio. So the cosine of angle A is your adjacent over your hypotenuse. We are going to say that our cosine of A is the same as in this triangle, AC over AB. And then we will take the inverse cosine of both sides of this function in order to get the A value by itself. So by taking the inverse cosine of the adjacent over the hypotenuse, we will get the measure of angle A. So the inverse cosine of AC divided by AB will get us the measure of angle A. And then finally over here we have tangent. So remember, tangent is our opposite over adjacent. So the tangent of angle A is always opposite over adjacent, and we'll fill in the sides that we know. So our opposite side is BC and our adjacent side is AC. We'll take the inverse tangent to get the angle A by itself, because tangent and inverse tangent are inverse operations and they will undo each other. And then we'll have to take the inverse tangent of BC over AC. So that means that the measure of angle A will be equal to the inverse tangent of BC over AC. So we'll do this with some actual values to hopefully solidify what we mean by this. So in this example it says let angle A be an acute angle in a right triangle. Approximate the measure of angle A to the nearest tenth. So since we're given that sine A is equal to 24 hundredths, we just want to get the measure of angle A alone. So that means I'll be taking the sine inverse of this entire function. So sine inverse of sine A will equal the sine inverse of 24 hundredths. This is the value that we'll put into our calculator. The inverse sine and the sine function cancel each other out, so we're just left with the measure of angle A, and the value that we get is 13.9 degrees. Remember, we're talking about it's finding the angle of a triangle, so we put that degree symbol when we find the measure. For this one, we will need to take the inverse tangent of A to get A alone, which means we'll need to take the inverse tangent over here of 1.73. So that will get us the measure of angle A. You plug that into your calculator using the tan inverse function button, and we get 59.9, which 98, so it rounds up to 60.0 degrees, or just 60 degrees, you can write. And then finally, we have the cosine of A is 62/100, so we will get rid of the cosine function by using the inverse cosine. The cosine of A and the inverse cosine will eliminate each other, so we're just left with the measure of angle A equals the inverse cosine of 62/100. And when we enter that side, the right side of that, into the calculator, we will be left with 51.7 degrees for the measure of angle A. So these were, of course, measure of angle A in 3 different triangles. They can't all be that same amount, but they're all that measure in a different right triangle there. So then we have this example that says find the acute angles of the right triangle and round to the nearest tenth if necessary. So I want to first find the measure of angle R. So that means my angle R will be my theta. So the sides that I know that are surrounding theta, well, I've got 13, which is across from the right angle, so that's my hypotenuse. And I have the side that's next to it, so that's the adjacent. So because I know my adjacent and hypotenuse, I'm going to use the cosine of R to set up my function here and figure this out. So I don't know the cosine of R, so I'm going to leave it like that. But the adjacent side is 5 and my hypotenuse is 13. To get R alone, I just have to take the inverse cosine of both sides, and that will get me the value of the measure of angle R. So when we put that into the calculator and we round to the nearest tenth, we are left with 67 4/10 degrees. So at this point, when you want to find the measure of angle M, you have 2 options. You can either take 180, subtract the 90-degree angle we know, subtract the 67 4/10 angle we just calculated to get your difference for a measure of angle M, or, and to check yourself, you can use trig. So we can say the sine of angle M will equal the opposite over hypotenuse. Now the reason I'm doing this is because if I move my theta from angle R, since I found it, now I'm finding the angle M. That means 5 is my opposite and 13 is still my hypotenuse. So at this point I can use my sine function with the sine of M for opposite over hypotenuse. So that means I will write the sine of M equals 5 over 13, and I can take the sine inverse of both sides to get the measure of angle M by itself. That makes these 2 functions cancel, and we're just left with the measure of angle M. And then we take the inverse sine of this to get a result of 22 6/10, just like we had calculated above. So you can use that to check yourself, do it with trig, and then use the 180 minus all the angles to get that missing one and check. It's up to you which way you'd like to go. You can pause the video and try these if you'd like, and then press play when you're ready to listen to the results here. So for the measure of angle A, that is our theta. The side next to it is the adjacent, and over here is across from the right angle is our hypotenuse. So to find A, I'm going to be using the cosine of angle A equals my adjacent 15 over my hypotenuse 20. To get that A value alone, I need to take the inverse cosine of both sides of this function. When I plug that value into the calculator, I'll be left with the measure of angle A, which will equal 41 4/10 degrees. So at this point, you can either subtract from 180 all of the angles that you just found, and you can get your difference of 48 6/10. Or if you wanted to use trig here, we're now focusing on our theta being at angle C to find that missing angle. So 15 is now the opposite side, 20 is still your hypotenuse. So we'll now need to use the sine function, and we'll take the sine of C as the opposite 15 over the hypotenuse 20. I'm going to take the inverse sine of each side of this function, or this equation. So when I take the inverse sine of 15 over 20, I'll end up with the measure of angle C equaling 48 6/10 degrees. Then I'm going to find the measure of angle R and T in this next triangle. So again, I'll start by labeling my theta. 10.8 is the hypotenuse, and in this case, our 9.4 will be the opposite. So to find r, I'm going to have to use the sine function. The sine of r will be your opposite 9.4 over your hypotenuse 10.8. We'll take the inverse sine of both sides of this, and we'll say that the inverse sine of 9.4 divided by 10.8 will get us the measure of angle r equaling 60 and 5/10 degrees. To find the measure of angle t, we want to move theta. So our theta is now up here at angle t, which means the side next to it is now the adjacent side. That 9.4 is no longer opposite, it is now adjacent. 10.8 is still your hypotenuse. This means we're going to be using our cosine function for the angle t, and that will be your adjacent 9.4 over your hypotenuse 10.8. We'll take the inverse cosine function of each side. So the cosine inverse of 9.4 over 10.8 will get us our value for the measure of angle t, since this inverse cosine and cosine cancel each other out, so we're left with 29.5 degrees. You could take 60.5, 29.5 plus 90, and it should all add up to 180 to check your work. Finally, we're just going to kind of take this one step further. In some cases, you're going to see the directions that say solve the right triangle. So what does that mean? It just means you have to find all the missing sides and all the missing angles. So if you know two of the side lengths, you can just use Pythagorean theorem to find the third side. That's something we already know, and we won't need to use trig. But if you only know one side and one angle, you can use the trig ratio to find the other two sides. If you know one acute angle, you could use the triangle angle sum theorem to find the third, so just subtract from 180 until you find your remaining angle. Or if you know the lengths of two sides, you can use an inverse trig ratio to find the acute angle measures. So when we take a look at this first triangle, we can see that we know 3, 8, and we don't know this last side. Well, 3 and 8 are the legs of this right triangle, so we can use the Pythagorean theorem here and do 3 squared plus 8 squared will equal c squared to find that value for wy, that hypotenuse of this triangle. So 3 squared is 9, 8 squared is 64. When we add them together, we are left with 73. So we'll take the square root of both sides in order to get that c value by itself, and we're left with the square root of 73 for that missing hypotenuse. So now we know all three sides, and we know one angle is 90 degrees. We need to figure out what are these two other missing angles. So to find the angle W, I'm going to mark that as my theta. 3 is the adjacent side to it, and 8 is the opposite. That means I can set up my tangent function because it uses opposite over adjacent. So the tangent of W will be my opposite side 8 over my adjacent side 3. So in order to get W alone, I'm going to take the inverse tangent of both sides. When I do that, it allows my my inverse tangent and my tangent to eliminate one another. And we'll be left with the measure of angle W over here. And when we plug in tangent inverse of 8/3 to our calculator, we get 69 4/10 degrees. So to find the measure of angle Y, you could use the tangent function again and use inverse tangent to find that. Or you could just take 180 minus 90 minus the 69.4 we just calculated to get your difference of 20.6 degrees. Finally, in the last example, we can see we know one leg. We don't know another, so we won't be able to use Pythagorean theorem this time. But we do know one of the acute angles. So since this one's already 90, this one is 30, that means that this last angle K has to be 60. I'm going to use 30 as my theta here and mark what my sides are. The 4 would be opposite. The JK is our hypotenuse, and JL is our adjacent. We are going to take and find that side JL first. So if I want to find JL, I'm using opposite and adjacent there. So that's going to be my tangent function. The tangent of angle J will equal the opposite over the adjacent. So let's plug in what we know. Angle J is 30, so we'll take the tangent of 30 degrees, and we'll set it equal to the opposite 4 over the adjacent, which is x. We will solve this by multiplying by x on both sides. When we do that, we'll be left with x times tangent of 30 equals 4. So we'll just need to divide by the tangent of 30 on each side. That will leave us with our x by itself, and we get a value of 6 and 9/10. So that means our JL adjacent side length is worth 6 and 9/10. So at this point, you could use Pythagorean theorem, but since we had to round this, that's not going to be super precise for us. So I would suggest using a different trig function instead. So now we can consider, well, we know that our opposite side is 4. And we're trying to now find the hypotenuse. So we're going to try to use which trig function will take the opposite and the hypotenuse in comparison to another. So that'll be our sine of j would have been opposite over hypotenuse. J is 30 degrees. The opposite is 4, and the hypotenuse we'll call x this time. Again, multiply by x on each side, which eliminates our denominator. X times the sine of 30 equals 4, and to get x alone, we'll divide by the sine of 30. When we do that, we are left with x equals, and we end up with a nice whole number of 8. So if you had done Pythagorean theorem there, you might have ended up with a little bit more of a decimal. That's why we wanted to be very precise, since we had found 6.9 first, and that was a rounded answer. We don't want to use a rounded answer in another part of the problem because it might affect the outcome of that part. So those are how we would solve our right triangles using those inverse trig functions.